Hello, my name is Jack, and this is quantum tunneling and its applications. So, I'm sure you're wondering, what actually is quantum tunneling? That's a great question, but I'm going to answer your question with a question. So, if we have this guy here, and he rolls the ball down this hill, where's it going to end up? I'll give you a second to think about it. Well, if you said it's going to end up at this X, you would be correct, right? In terms of classical physics terms, the energy in the system is going to be the energy out of the system, right? We can't get any energy to get over this hill, and that's called a potential energy barrier, right? To increase your potential energy, this ball would need to be higher, right? It'd need to be higher than that hill to be able to get over this potential energy barrier, but because the potential energy right now is lower than what would be needed to get over the hill, we have something that's called a potential energy barrier. So, what's happening in quantum tunneling is that this ball is basically going to roll down this hill, and then it's going to hit this X, and then it's just going to appear on the other side of the hill. I'm sure you're wondering, how is that possible? And the short answer is nobody 100% knows. We have seen it just appear on the other side, but the big idea of quantum tunneling is that a particle is overcoming a potential energy barrier and appearing on the other side of this potential energy barrier. Basically, where classic physics would not say it's possible. Quantum mechanics says it's possible. But the big idea is the wave function. And we need to model that ball from the previous slide as a wave function for this to work. A lot of this is mathematical. So what we're saying about this wave function is that the high points are going to be where it's most likely to be, where this particle most likely is, and then it's going to go through these three phases. So the first phase is just, it's untouched, right? It just could be somewhere within this wave, this function, somewhere here. The second part is the interesting part. We're from this 0 to L. Now this is a potential energy barrier, right? We can see the potential energy needed is a lot higher than what this particle has. And so we know that it's not just going to be able to get over it. It needs to tunnel, which it does in this second part right here. It tunnels through and exponentially decays. And what that means is the probability that it's going to be on the other side exponentially decays because because of this barrier. It's going to exponentially decay. And then on this other side, this third side, is the probability of where this particle is going to be. So we can see it's probably right here, right at the high point. That's most likely where it's going to be. And one important thing to note is that this is not representative of energy, but this is representative of probability. And that's like really important, right? Like the ball that's appearing on the other side is the same ball. Like it didn't get smaller, it didn't get bigger. It's the exact same ball. And so that's a big idea, right? This particle that's going in is the same particle that's coming out. It's just the probability that it's going to happen is extremely low. And I'll just go ahead and explain the equations. So we basically get this equation where this lambda over 2, this symbol over 2 is going to be here, but it's going to equal this big equation, and we can see that this is actually going to give us a percentage because it's 1 over everything. So we get like a percent chance of this particle tunneling, and what the percent chance is that it's going to be on the other side. And we can see a big part of this is going to be the energy and the potential energy, right? So if that potential energy barrier is really, really close, to what the potential energy of this particle has, you're going to get a way higher % chance that it's going to tunnel its way to the other side. And some of the applications that we've actually found for tunneling is the scanning tunneling microscope. And basically what it is you have this tiny metal tip, and what you're doing is you're getting really, really close to something, like super, super close. And what that's going to do is that's actually going to reduce your potential energy barrier to very, very small, right? Because you still need energy to make it from, like in this diagram, you still need the energy to make it from this conducting sample to the metal tip. And we can see that the electrons are tunneling either from the sample or the tip, but they're going from the sample to the tip. And so we can use that actually to map surfaces. And that picture on the left is actually a picture that we've used using the scanning tunneling microscope. But yeah, so from this diagram, the electrons are going to tunnel and get to this metal tip. And that's the big idea. It's very close, so it's going to tunnel and get there, and then it's going to show up. We also use it in electron microscopes. It's not directly related, but it's kind of the same thing, right? We're shooting electrons at an object to get a picture, just like the other one, right? We're using the tunneling specifically to get the pictures. And yeah, these are my sources that I use. I would say, in conclusion of all of this, quantum tunneling is pretty crazy, and also a big idea is that it's all probability based. This is not, like, you're not getting any physical answer out of these equations. Like in other physics, you might get a physical, like, acceleration, velocity, position, like you'll get something. This is just the probability that it's going to end up on the other side. And it's not traveling at a speed, it's just appearing there. But yeah, thank you.